A product planner slides a spec document across the table. The developer slides it back. The feature delivered looks nothing like the feature requested. In the post-mortem of a failed software project, the culprit is rarely a technical limitation. Most budget overruns and critical bugs start as a simple misunderstanding between the person who wants the feature and the person who has to build it. The problem stems from a cognitive gap. Business planners speak in needs, what the user wants and why they want it. Developers, however, build logic gates. They require binary, structured requirements, what the system physically does. Take this standard product request. When the app goes offline, it should quickly encrypt and save the user's data so they don't lose it. To a human, that makes perfect sense. To an engineer, it's a structural liability. Who is encrypting the data, the user's device or the server? What exactly is the threshold for quickly? And if the save fails, what happens next? The sentence collapses the moment you try to code it. Natural human language, with all its context and nuance, becomes an active threat in system design. To bridge the gap, vague ideas must be transformed into a strictly enforced engineering contract. We fix this by running everyday language through a rigorous engineering pipeline, stripping away the ambiguity by forcing it into a standardized skeleton. The ISO 29148 standard breaks system behaviors into 5 mandatory parts: condition, subject, action, object, and constraint. Forcing our offline requests through this tree makes flaws immediately surface. The sentence gave the action to an invisible entity. The system doesn't know who is responsible. To handle the specific timing and triggers of that action, engineers use the EARS methodology, the easy approach to requirement syntax. EARS locks down logic using capitalized keywords. While defines the network state, when captures user action, and the system shall mandates the physical response. By requiring an if-then pattern, you dictate exactly what the application must do if encryption times out and fails. Forcing language into these strict skeletons removes all assumptions. It translates a vague feature request into a physically mappable system state. Once the skeleton is built, we pass it through the INCOSE quality rules, a final filter designed to make the statement mathematically verifiable. First, we eliminate passive voice. A requirement cannot state that data should be saved. It must declare that the local storage module shall save the data, pinning undeniable ownership to a specific architectural component. We eradicate subjective adjectives, replacing unmeasurable words like quickly with rigid thresholds like 500 milliseconds. We enforce the single thought rule, splitting compound sentences so QA testers can pass or fail actions independently. Finally, we remove escape clauses. Machines need absolute boundaries, not if necessary. Look at the contrast. When the app goes offline, it should save quickly becomes, while the device is offline, the mobile client shall encrypt the session payload within 500 milliseconds. It is dense, specific, and unambiguous. This transformed requirement functions as a mathematical boundary for the software. It forces intent and execution into alignment. In modern software development, this strict rigidity often clashes with Agile methodologies, which favor simple conversational user stories, statements like, "As a user, I want to save data offline." User stories effectively explain business value to humans, but completely fail as system blueprints. The solution is a hybrid. The user story defines the goal at the top, while strict EARS syntax sits underneath as mandatory acceptance criteria, detailing exactly how the system operates. This modern practice is called agreement engineering. It moves teams away from simply writing documents, forcing a disciplined methodology that builds a shared, objective understanding of the product. As development evolves, this strictness enables higher levels of automation. Constrained language provides the precise logic required for AI coding assistance and automated testing frameworks to parse and execute instructions without human intervention. Mastering requirement syntax isn't about polishing a document. It is the work that prevents failure before the first line of code is ever written.